Hi. So let's start today with the concept of tree. So the first question is, why do we need the concept of tree in embedded, right? So in embedded, we are also focused on saving the data in our memory. So you if you see your mobile phone, you want to save your images and everything in a memory space. So there, if we have a requirement that we want to retrieve, save the data and also retrieve the data, so the retrieval of data should not take longer time, right? So it can happen that you are saving one data one by one many datas, and when you want to retrieve a particular data, it should not go one by one and check for the data, and then when it finds it, it should give you. So just think of the scenario where you want to send, let's say, 1 crore data or 1 crore data point for any particular thing. So that time it will be very beneficial to use the concept of tree in embedded to store the data into memory location. So normally what we use structure, and we create an array of that structure, and then we can save that in that array. But the problem with the array is that with that array we can have a maximum limit, and also that array should have an index number. So if I want to get the element at index 1, it is easy to get, but if I want to search an element that is located at the last index, then it can take a long time. For this we will be using the concept of tree, how to store the elements in the memory efficiently so that the retrieval and also storage of that element becomes easy. So for use case scenario, I can give, let's say we have a sensor connected, like a temperature sensor. So whenever our temperature goes up, we want to record the data of the temperature plus the timing. So now, if I tell you that when the highest temperature occurred, so you may be recording this temperature at an interval of 10 seconds. So after one day, if I ask you what is the maximum temperature, then if you save in an array format that whatever data it's coming, you are saving randomly, then you need to run a loop to verify and compare each element, which is the largest data or which is the lowest data. So this will take a long time, right? So this is actually a requirement in industry, where if you want to save the temperature and time in a particular manner, so that the highest temperature is always stored at the first and the lowest temperature stored at the last, or you can directly access the lowest and the highest temperature without much difference in time, then we actually need to use the concept of tree in embedded. Now from interview perspective, this question is asked in Amazon, in Google, and in Microsoft. So for Amazon, there are embedded devices like Alexa and all. For Google, we know there are a lot of embedded works going on. And for Microsoft, it's very important that they make computers, so they want to store it in a more efficient way. So they use this tree algorithm to save the data. Okay, now let's move to the concept of tree. Okay, let's now see. We have a data of temperature recorded after every 10-second interval. And so we want to arrange the data in the using the concept of tree, so that the insertion and retrieval of data becomes very easy, and to get which is the maximum element, which is the minimum element, also very easy. Okay, so let's understand first the tree. So basically, what does tree have? Tree have branches. So if I draw a tree, then tree will have a branches, and then tree will have leaves, right? And there will be nodes in the tree. So same concept we will apply. So leaves are the end part of the tree. After the leaves, there is no more branches or node, and if there is a node, then there should be a leaf or a branch, correct? So we will use that concept. So let's remember that concept and focus on it. So let me just make the tree first, and then I will explain it to you. Okay, now let's understand how I arrange this number. So you can first have a look at this and think for a moment, how did I arrange it? Okay, now let me explain. So when I get the first element, that is 10, I place the first element here. Then when I get the next element, I just check if the next element is higher than 10 or lower than 10. Since 15 is higher than 10, I placed it on the right hand side of 10. Then I check the next element, that is 25, whether 25 is greater than 10 or less than 10. So it is greater than 10. So I move to next 15. If it is greater than 15, I move to next and I placed it next to 15. Then I see the 33. Same approach, and 33 is placed here. Now I check whether 8 is greater than 10. No, it is not. So I start placing it on the left hand side. So I placed it on the left hand side. And then I see 7. So I place 7 on the left. and then I see 4. So 4 is less than 10, less than 8, less than 7. I placed it 4 at the leftmost side. Then I find 12. So now let's see how I place 12 in this position. So 12 is less than 10. Yes, it is. So sorry, 12 is greater than 10. Yes, it is. 12 is less greater than 15. No, it is less than 15. So it is placed on the left hand side. Now 19. So 19 is greater than 15. Yes. 19 is greater than 25. So you will say yes, 19 is greater than sorry, less than 25. So it should be placed here. So after 25 we should place it instead of placing it with 12. So I made a mistake. So it should be linked with 25. Next is 17. So 17 is greater than 10. Yes. 17 greater than 15. Yes. 17 greater than 25. No. 17 greater than 19. No. 17 less than 19. So it is placed on the left hand side. Similarly, 11 and 9 are done in the same manner. You can check it. So like 11 is greater than 10 but less than 15, less than 12. So it is here. Similarly, 9 is less than 10 but greater than 8, so it is placed here. Okay. So I hope this arrangement is clear to you guys. So I have applied a simple rule. So whatever is the first element, that should be considered as root in the tree, and whatever will be the next element, we have to check if that element is greater than root. Okay, so if I check that element as I, so I need to check if I is greater than root or I is less than root. If so, the condition will be very simple. I less than root, place on the left. I greater than root, place on the right. So what I can do is, every time when I go to the next node, okay, then I will consider this as a root. Okay, so if I go to 15, then 15 will become my new root and I will just compare the element with it. Similarly, if I go to 25, I will compare it as a root and I will compare the element with it. So what benefit actually we are getting from it? So look at it. If I want to retrieve the minimum value from this, okay, from the minimum value, so what I need to do, I just need to start from the root and go all to the left only. No need to look at the right, I only need to go to the left. So what is the left? Till I reach a point that there is no more element in the left. So what is the left of 10? 8. What is the left of 8? 7. What is the left of 7? 4. So 4 is my minimum element available in this entire data set, correct? So and these last elements, that is 4, 11, 7, 33, these are called leaf nodes. Or I can say leaf nodes, because these are the last part. So these are leaves, so it is called leaf nodes. And these individual areas are called you can say these are nodes, and these are the branches of the nodes. Okay, and the initial starting is the tree. Now similarly, so the element we need to go, so we can say that go to left until leaf node available. Okay, so if we go to the left until the leaf node, then we get the minimum. Similarly, for the maximum element, it is the same thing. Go to right of the node until leaf leaf node available. Same thing. So if I go all the way to the right, then I already reach 33, so we get it. So this is the concept, right? So here you see that every time if you want to find the maximum or the minimum, it is very easy to get. To follow one simple algorithm without copying or without comparing, we will reach that location. And also, if I tell you I need to get the data that is present at node number, let's say 12. So what I can do, I can start from this element 10, and I can just say that I can, when I want to reach to the node 12, what I want to do, I just want to compare. So 12 is greater than 10, so it should be on the right hand side of 12. Go to the right hand side. So 12 is greater than 15. No, go to the left hand side. So I get 12. So it is always a check comparison when we are reaching one node to another. So in this manner, I can reach 12 in 1 2. Third step, I can reach 12. Now I want to reach 17. Since 17 is at the end, how many suppose if I want to get to the 17, then how many steps I need to compare? 1 2 3 4 5 6 7 8 9. Normally 9 steps we need to compare. Now some of you might say that let's arrange this in an ascending order or a descending order, like shorting it, right? So let us short the thing. So it will start from 4, 7, 8, 9, 10. Then it will be 11, 12, 15, 17, 19, 25, and 33. So if I want to get to the 17 from a sorted array also, then I need to check 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 comparison has to made in order to reach 17. Otherwise, you can also do a binary search. Since it is a sorted array, still with a binary search also, if you see, you will first compare the middle of it. So the middle is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 6 will be the middle. 1 2 3 4 5 6 7 6. So 6 one comparison you made here. Since 17 is greater than the middle element, so you move this to here. Then again you come do one more comparison, 1 2 3 4 5 6. So third element you will take. So third element will be 17, and so you get to 17 after total 3 comparison. Similarly, here, if you want to reach to 17, how many comparison you need? You need 1, then 2, then 3, and fourth comparison. So, in some manner, in binary tree, if you want to see that you can reach an element at the shortest path possible. So, tree always gives you the shortest path possible, right? So, even if you want to reach to 9, it will take only 1, 2. To reach to 8, it will take you 1. To reach to 10, it will take the first element, like that. So in this manner, the elements will be arranged in the memory so that we can access it very quickly. So now let's see how in the code we can do it. Okay, I will be writing the code for the binary tree in C. So I am using Visual Studio. You can use any editor you like. So for that, we have to write in few steps. So follow the steps carefully and you will always remember it. So let's import the libraries first that I will be needing it. Okay, after the libraries are imported, we want to create the structure that will be using it as an element of our tree. So this is a binary search tree. Why we are called as binary? Because it has two element. Every node will have at least two element. Okay. After this structure has been created, we need to have a function that will create this node in the memory. So we'll write those function. So this function should return us the location where it created it, right? So it will return the pointer of that location of that structure, and we will only pass the argument as the value that we want to put into that location. So this is the line that will create a new node with in the memory location. So malloc will be called to allocate the memory of the size of that node. So that node has three parts. One is the value, one is the address of its left child, and address of its right child. Okay, currently we are creating a single node, so we will assign this addresses as null. And we will assign the value as the value argument that we have passed. And finally we will return the address of the newly created node. So our node creation is successful. Then we want to write a function that will insert the node. Always remember to write comments. It will be easy for you to remember in actual interview sessions. After inserting the node also, we also want to return the location of the node where we inserted. So we will copy the same structure, change the name, but we also need the location where we want to insert a new node. So we want the address of it, root address. So first we want to check if the root is null. Null means it is a first element in the node. So we want to check if the root is null or not. If the root is null, then we want to insert the element that we create in that particular location. So we'll call the create function and pass the value that we want to insert. Now, if the root is not null, okay, then it can either be greater than root or less than the root value. Okay, so we will check it if value is less than, or it can also be equal to if we consider there is a duplicate case. Let's consider that. So if the value is less than or equal to root.val, then we know that if it is less than, then we want to create the node on the left hand side. So we want to pass root dot left. In the left we want to make the entry, so we will again call the insert node function. So I will be inserting the node in a recursive manner. So I will be putting it in the left node. So now what I did is, I know that this value is less than the root node, so I want to put it on the left hand side of the root node. So I made the left hand side of the root now as the new root, and I called that function. So this one here is a root currently considered as the left hand side, and I will be passing the value to be inserted on the left. So recursively it will be again checked and verified. Now there will be another condition, else this is greater. So this condition can only one more condition, that is it is greater, so it can be entered on the right hand side. Okay, finally this is done. So we need to return the location of root, and now this is done. So we have created the node, inserted the node, and have a function that will return as the maximum value and the minimum value. So max value, let's say we want to search the max value, so we want to return the integer, find max. So we'll pass the root only. So to find the, so we will take care of a corner case, that if root is equals to null, then we don't have any element. In this scenario you can return something like -1 to signify that there is no element. Else what we want to do is, we want to traverse the tree all the way to the left till we find a leaf node. So else, if we have root left of it, so we are finding the max, so we should look into the right. So right of it equals to null, that means this is the rightmost, and we will return the value of the current root. If it is not null, then what we need to do, we need to recursively call this same function. So that will be return root, find max, and we will pass root right. So finally what we are doing, we are passing a root, we are checking if it is a null, then we are passing -1, that it is a corner case. But now we are just checking if the root that we have passed is having any right element or not. If that right element is not, that means there is no more root, there is no more branches on the right hand side, so we'll pass the value of that same root, because that will be the max value. Now, if there is some root node present, then we will pass that root node till we reach this point where we have no more root present on the right hand side, and we will just return this value. Okay, so that way we will find the maximum value. Similarly, let's copy it and just change it. We will find the mean value. So we'll find the mean value to the left of the root. Mean and max value we can print from it. Okay, so let's now write the main function. Okay, so I have added the body of the main function. To save time, I did the coding. So now just I have added one array here of random numbers. Then this is the length variable that I want to get the length. So this part is required only to put the values inside the root or inside the binary tree. So I have called this function which will be inserting the values in the root and one by one using this array, and finally we want to print the maximum and minimum value in this. So let's run it. So I have entered those numbers. Now let's run it. See, the minimum number it is giving as 9 and the maximum it is giving as 33. I think some mistake is here. So why it is giving 9 as minimum, it should give 4 in the minimum. Okay, here I have called by mistake max, it should be mean. Okay, okay, so I get 4 and 33. Okay, so I hope this is clear to you guys that this is how the binary tree works. Okay, and in the next video we will see how to search an element and how to delete an element from a binary tree. Thank you.